Hello student, I am Latif sir. Today I will discuss about the first chapter of class 12 chemistry, the solid state. We know that depending upon the intermolecular force of attraction and intermolecular spacing, matter can be classified in three classes: solid, liquid and gases. In this chapter we will learn about only the solid state. Let's see what is solid. Solids are rigid substances having a definite shape and volume. They have higher density compared to liquids. This is because in solid the constituent particles are held together by strong intermolecular force of attraction. That's why they do not allow them to have translational motion. They can only vibrate and rotate about a fixed position. Now, types of solids. Mainly there are two types of solids: crystallines and amorphous. In this chapter we are interested only with crystalline solids, but here you have to read the differences between crystalline solids and amorphous solids. Let's see the first point. Crystalline solids have definite and regular arrangement of constituent particles, while amorphous solids, they does not have any regular arrangement of constituent particles. Second point, crystalline solids are true solids because they have a regular arrangement of constituent particles, while amorphous solids are sometimes called supercooled liquid or pseudo solids. This is because amorphous solids do not have any regular arrangement of constituent particles. Third point, crystalline solids have long order of arrangement of the constituent particles, while amorphous solids have short order arrangement of constituent particles. And the last point, and the next point, crystalline solids are anisotropic in nature. That is their physical properties like refractive index, electrical conductivity are different in different directions, while amorphous solids are isotropic in nature. That is their physical properties like refractive index, thermal and electrical conductivity are same in all direction. Then the last point, crystalline solid have a sharp melting point, while amorphous solids melt over a certain range of temperature. Now, types of crystalline solids. Depending upon the nature of constituent particles and bonding nature, there are mainly four types of crystalline solids. First, ionic solids, covalent solids, molecular solids and metallic solids. In ionic solid, constituent particles are positive and negative ions. For example, in NaCl, the constituent particle is Na plus and Cl minus. Second one, in covalent solids, the constituent particles are atoms. For example, in diamond, all constituent particles are carbon atom. Third, molecular solids. In molecular solids, the constituent particles are molecules. For example, in water, in ice, in solid, in ice, constituent particles is all constituent particles are water molecules. In solid carbon dioxide, constituent particles are carbon dioxide molecules. And in metallic solids, the constituent particles are metals, ions and free electrons. Second point, bonding force. In ionic solids, the bonding force are electrostatic force of attraction. In covalent solids, the bonding force are bonding nature is covalent bond. In molecular solids, the bonding forces are van der Waals force of attraction and dipole force of attraction. And in metallic solids, the bonding forces are electrostatic force of attraction between the positive and negatively charged species. Now, melting point. Ionic solids have high melting point. And covalent solids have very high melting point. Molecular solids have low melting point, and metallic solids have moderate to high melting point. Now, conductance. Ionic solids are conductor of electricity in aqueous solution also only, but in solid state they cannot conduct any electricity. Covalent solids are non-conductor of electricity because they do not have any ions in solid and aqueous solution. Molecular solids are also insulator, they cannot conduct electricity, and metallic solids are good conductor of electricity due to presence of free electrons. And the last example of ionic solid NaCl, example of covalent solids diamond, example of molecular solid water vapor, water, solid ice, solid, that means ice, and dry carbon dioxide, that is solid carbon dioxide. Hmm. And metallic, example of metallic solids copper, iron. Now what is crystal lattice and unit cell? We know that in solid, crystalline solid, the constituent particles have a regular or periodic arrangement, and the constituent particles are generally represented by points. You can see this is a two-dimensional crystal lattice, and what is crystal lattice? A periodic arrangement of points is called a lattice, and each point is called a lattice point. These are, each point is a lattice point, and this shows a two-dimensional crystal lattice. And the small box, which if you repeat again and again, you will find, you will describe the entire lattice, and this small box is known as unit cell. So the smallest geometrical portion of the crystal lattice, which can be used as repetitive unit to build up the whole crystal, is called unit cell. This one is unit cell. This is a two-dimensional crystal lattice. Now types of unit cell. There are mainly 4 types of unit cell: simple or primitive unit cell, face centered, body centered, and end centered. In simple or primitive unit cell, the constituent particles are present at the corner of a cube, only at the corner. In face centered unit cell, the constituent particles are present at the corner and at the midpoint of each 6 faces. Okay, so in face centered unit cell, constituent particles are present at the corner as well as at the center of each of 6 faces. You can see this is the picture of face centered. Now body centered. In body centered unit cell, the constituent particles are present at the 8 corner of the cube and at the midpoint of this unit cell of this body. Okay, and in end centered unit cell, the constituent particles are present at 8 corner of the cube and 2 constituent particles are present at 2 opposite faces. Okay, now calculation of number of particles per unit cell. Here you have to remember that the particles present at the corner is the part of 8 such unit cell. That's why the contribution of this unit lattice point or particles to this unit cell is 1 by 8, and the particle present at the faces, the particles present at faces are the part of 2 such unit cell. That's why the contribution of this particle to this unit cell is 1 by 2, half. That is this is because this particle is shared between 2 such unit cell. Okay, and the particle present at the midpoint of unit cell is only part of this unit cell, not shared with any other unit cell. Okay, so before calculating, you have to remember this. So in simple cubic unit cell, there are 8 particles present at 8 corner, and each particles are shared between 8 unit cells. So contribution of this particle is 1 by 8 to units to this unit cell. So there are 8 unit cell, so 8 into 1 by 8 equal to 2, equal to 1. So total, and there is no phase particle present at face and center. That's why no contribution from face and no contribution from center. That's why in simple cubic unit cell, the total number of particles present is 1. In face centered, there are also 8 particles present at 8 corners. So 8 into 1 by 8 is equal to 1, and 6 at 6 faces present, 6 particles are present, and each particle is shared between 2 unit cells. So 6 into half, that's is equal to 3, and there is no center particle present. So total 4 particles present in face center unit cell. In body center there are also 8 particles at 8 corners, so 8 into 1 by 8 is equal to 1, and no particles present at face, and 1 particle present at the center. This is completely a part of this unit cell, not shared with other any unit cell. So total number of particles is 2 in body center unit cell. In end center unit cell there are also 8 particles at 8 corners, so 8 into 1 by 8 is equal to 1, and 2 particles at the opposite faces of this unit cell, so 2 into half is equal to 1. Total number of particles present is equal to 2. In the next video, next lecture, I will discuss about the different type of crystal system.